All right, so now I'm going to use the computer program R to program this iterative method that's being discussed here in an example where my data are from the Poisson distribution. Okay, so just as a reminder, I'm going through this paper by Nelder and Wedderburn. The complete playlist I'm making for this paper and the link to the paper are in the description of this video. Okay, so let me go ahead and go to my Blackboard here. So previously, I discussed that Z, that's our outcome data. It's Poisson distributed. Y is equal to beta times X. So we have our covariates X. Beta is what we want to estimate. This is our unknown parameters. And then we're going to use the canonical link to link that random distribution to Y, where theta equals the log of lambda. Okay, this is based off of rewriting the Poisson distribution as an exponential family type distribution in step 1 of this example series. So I'll include the link to that also in the description of this video. And then in step 2, we found what W and Y are for the iterative weighted least squares. Basically W, we saw that it simplifies to being just d mu dy. It's pretty much always the case when you have canonical link, which is something I think we'll discuss more in the next section of the paper. And so we have mu equal to e to the y. All this was shown in the second step of this example. And so now we need to go ahead and first we need to remember if W is, instead of writing it sub k, right, because there's a different W for every observation from k equals 1 to n, right? So if we make W into a diagonal matrix, I can find the solution to a weighted least squares using matrix notation, and this is the solution right here. We're going to need this as we go into programming this in R, but I just want to briefly kind of talk through what it is we're going to do in R, and then I'll make it that make a little more sense hopefully. So we'll start with we have our Z's, so we're going to go ahead and generate some Z that's from the Poisson distribution, and I'll just generate some X values, and I'll go ahead and assign a beta, but we'll have to figure out how to estimate it. Okay. So when beta is unknown, we don't know why. So there's the starting method that's discussed in the paper down here, which says go ahead and use the first approximation of mu. Go ahead and set it equal to Z, but you do need to be careful with extreme values. Okay, so we'll go ahead and set mu equal to Z plus 0.05. Just so that when we have zeros, it doesn't mess up our calculations, because that would be an extreme value. So yeah, we'll just go ahead and set mu equal to Z plus a little bit more to make it so we don't have any zero values. That'll be the first thing that we'll do. And then once we have that mu, we'll be able to find d mu dy, and we'll be able to figure out weights. So we'll have that diagonal matrix of weights, and then we'll be able to figure out this lowercase y, based off of what mu is, and d mu dy, and capital Y will, let's see, what will we set capital Y to be first thing? Yeah, so capital Y, well, I guess we can just take, if we know what mu is setting it equal to Z, so we'll just take the log, and that's what capital Y will be. Okay, so for our first step, capital Y will just be the log of mu. Okay, and then from there, we'll have this lowercase y, which will make up right here. We'll have our weights. We know what X is. These are our covariates. So we'll be able to obtain our first estimate of beta. Once we have our first estimate of beta, now I can estimate Y, okay, using that estimate of beta. And then once I have an estimate of Y, I can find mu, d mu dy, w, y, etc., go ahead and figure out an updated estimate of beta, plug that back in, a new estimate of y, etc., until basically beta stabilizes. All right, so that's what I'm going to do in R. Okay, so let me go ahead and pull up R. Okay, so the first thing I'm going to do is go ahead and clear my environment. And then I'm going to go ahead and simulate my data. I'll have a sample size of n equals 50. My beta is just -1 and 1. And then for my x data, I'm just randomly sampling the numbers 1 to 5 with replacement. I'm creating a matrix of x values where I have the intercept is just 1s, and then the next, and then my x1 variable. And then y is x times beta. Okay, so remember, I don't actually know beta. This is just for simulation purposes. Okay, so you can see over here what's going on. So I have the canonical link that theta equals y. And then I have lambda, which is the exponential of theta. Okay, and so I want to start with simulating z. So this is just random Poisson with that n and lambda. All right, and then I'm going to use the built-in GLM function in R to find my estimates of beta. All right, let's see what it found. -0.876 and positive 0.973. Okay, so now I would hope that the method in the paper by Nelder and Wedderburn will give me those same estimates. Okay, so I'm going to add 0.5 to mu. I could have just found the zeros and added 0.5 just to the zeros, but I found that it actually doesn't matter if I just add 0.5 to everything. And since I'm a lazy coder, that's the way I'm going to do it. Okay, calculate y, which would be the log of mu. Which we discussed, right here. So you take the exponential, so you just take the log. All right, and then d mu dy, and then that diagonal function of w's, of weights. Okay, and then set little y to capital Y for that first step, right? And then now I can go ahead and find my first estimate of beta. All right, and now I'm going to have a while loop, which basically does the same thing over and over again until my beta, the difference when I update the beta, it basically doesn't change very much. It changes less than 0.001. Okay, and you could adjust that to even be less than 0.00001. I just kind of chose that number arbitrarily. But you can see that I'm saving my previous beta. I'm updating y, mu, d mu dy, w, y, and then I'm basically finding a new estimate of beta. I'm going to print it each time. Okay, and this code, I'm going to include this code in the description of this video so that you can do this yourself. But we can see that, let's see what happens here. Let me, I'm going to try to make this bigger so we can see it a little bit better. So I want to make sure I get these exact same numbers that the automated, or the function that R already has, GLM. I want to get those same estimates. And if I look here, I can see I have the same estimates. So it's good, means that the code or the the way that we're doing it, or the way that's described in Nelder and Wedderburn's paper, is the same, or it arrives at the same answer that the function GLM that's built into R uses, or arrives at the same answer as that one gets.